Welcome back everyone. In last class we started free vibration of a single degree of freedom system. In today's class we are going to study how to obtain response or the free vibration response of a damped system. As you know, in reality most of the structure would have some amount of damping, and in some cases we can ignore it if the effect of damping is not much, but realistically damping need to be considered in the response, and we are going to see if we have a damped system, then how do we obtain the expression for the displacement and the amplification factors related to displacement. Okay, all right, so let us get started. What we are going to study today's class. Last class we saw that uh, what is the equation of motion, and what is how we saw how to solve the equation of motion for a undamped free vibration, right? So we said that the equation of motion for undamped free vibration is nothing but this, and then we saw that the response of this, okay, can be represented in terms of initial conditions as u0 cos omega nt plus u dot 0 sine omega nt. All right, and we said that omega n is basically the natural circular frequency of the system, right? And we tried to plot the ut, and then we try to understand, discuss what is the physical meaning of each of these parameters. Now in this class today what we are going to focus on is damped free vibration. So it's still a free vibration, so the external force will still be 0. However, for this case there would now be a non-zero value of damping. Okay, so we are going to consider damped free vibration. Okay, now for damped free vibration we are going to consider a specific type of damping that I have previously stated. It is viscously damped system. Okay, so for viscously damped system, as I have previously stated, the damping force can be represented as a linear function of velocity. Okay, so that my equation of motion that I need to solve, it becomes mu double dot plus cu plus ku, that should be equal to 0, right? So now today we are going to solve this equation that we have here, and we are going to follow the same procedure. So again it is a second order, okay, linear homogeneous differential equation. Okay, and the solution would take the same form as the last class, so I can represent my solution ut as an exponential function e to the power lambda t. All right, so once I make that substitution back to this equation of motion for damped free vibration, okay, I will get as lambda square m, or just write it like this, m lambda square plus c lambda plus k should be equal to 0. Okay, now e to the power lambda cannot be equal to 0. Okay, that does not give me any feasible solution. So I'm going to equate this expression here equal to 0, and that is a quadratic equation. Okay, and from your from your previous knowledge, the solution to this equation can be written as lambda equal to minus c plus minus c square minus 4 km divided by 2m here. Okay, so denominator is 2m. If you have forgotten, basically I am trying to write the solution of the quadratic equation is as x equal to minus b plus minus b square minus 4ac divided by 2a. Okay, so I'm just correspondingly I've got this expression for the roots of this difference roots of this quadratic equation. Okay, I can further write this equation as minus c by 2m plus minus, and then I'll take that 2m inside the square root sign so that it becomes 4m square. Okay, or I can further write it as this minus k by m. Okay, so I've got two roots for the lambda corresponding to the positive and negative sign. Okay, now if you notice here carefully, I have a term inside the root here. Okay, now this term could be positive or this term could be negative, and that will determine actually what what kind of motion, resulting motion, the system would have. Okay, so let us consider the first case in which we say that, or we consider that the term under within that square root sign is actually greater than 0. So what I'm saying here, this term here is actually greater than 0. Okay, that would mean lambda has, or I can write my lambda 1 as, this is positive, so my lambda 1 and lambda 2 would be real. I'll get two real roots. Okay, so the first would be this, and lambda 2 would be again minus c by 2m. However, I'll have a negative sign here. Okay. Now, if you look at carefully, both these lambda 2, lambda 1 and lambda 2 are negative, would be negative values, because if you look at it here, I have minus c by 2m, and I have under whatever the term that I have under square root is less than c by 2m. Okay, because remember I have c by 2m here, but then I have another term k by 1 which is actually subtracting from it. So the positive term here is actually less than here. So this would again be a negative number here, and this would of course be negative because there is a negative sign here. Okay, so let us say that my two roots are actually minus k1 and minus k2, where k1 and k2 are like positive numbers. Okay, so the solution, as I said, for this type of equation is written as a linear combination of both roots. So I can write it as a e to the power lambda 1t plus b e to the power lambda 2t. All right, and for this particular case here, I can write it as a e to the power minus k1t plus b e to the power minus k2t. Okay, and if you look at this function, both e to the power minus k1t and e to the power minus k2t are exponentially decreasing function. So if I write it here, or if I try to plot this function here, I have u of t and then I have t. The function would look like something like this. Okay, all right, and like of course, depending upon the value of k1 and k2, if k1 and k2 are very large, it would decay very fast. If that they are not very large, it would decay much slower. Okay, so the rate of decay actually depends on the value of k1 and k2. Okay, however, one thing to notice here is that now my undamped or my damped system here, okay, when this condition is there, when under the term under the square root is actually greater than 0, I get two real positive, basically two real negative roots. Okay, I do not see any vibration. So do you see any oscillation here? Okay, if you plot u of t versus t, you see that it is just a monotonically decreasing function that goes to 0 at very large value of t. However, there is no oscillation about the equilibrium position, okay, which let us say in this case was u equal to 0. Okay, if it had like oscillation, it would be something like this. Okay, so for this condition I do not see any oscillation. Okay, so let us check the other condition. Okay, so in other condition I'm assuming my this quantity here is actually less than equal to 0. All right, so if it is less than equal to 0, I can write my lambda as, okay, minus c by 2m, and then, because this is less than equal to 0, I'll take minus negative or minus 1 outside the square root so that it becomes I. Okay, and inside term, the terms inside the square roots are a by m minus c by 2m square. Okay, so once I take minus 1 out and I get I, now I know that this is positive. Okay, and let us represent it with another constant, saying this is minus c by 2m, this is plus minus I omega d. Okay, we'll see the physical significance of omega d, but let us for the right now, for the time being, assume that this quantity here is represented by another constant omega d, where omega d is a positive quantity. Okay, a real quantity. Now using this, now I can write my solution as, for the ut, okay, remember that it corresponds to lambda 1 and lambda 2 corresponding to the positive and negative sign. So I can write e to the power e to the power lambda 1 to lambda 1t, and then b e to the power lambda 2t. Okay, if I substitute it here, I would get e to the power minus c by 2m plus I omega d t, and then plus b e to the power minus c by 2m minus, okay, omega d t. Okay, I can take e to the power minus c by 2m t term out. Okay, so that I get this one as, okay, and inside I'm remaining with e to the power I omega dt plus b e to the power minus I omega dt. And if you remember from your undamped free vibration, okay, when we tried to derive the solution for that, I know that I can write this term e to the power ix as sin x cos x plus I sin x, e to the power minus ix equal to cos x minus I sin x, and then I can, like, substitute this value, arrange this term. This would basically it would give me something like this. Okay, let us say another constant, cos omega dt plus d sin omega d of t. All right, now I know that what is the plot of this function, and I know that this is an exponential decreasing function. Okay, so if let us try to plot this function for the second case. I know that this function looks like something like this from my from the solution of the free vibration. It looks like something like this. However, it is multiplied with another term which is an exponential decreasing term. All right, so it is, I mean, it would be something like, let us say, uh, like this. Okay, so when you multiply it, the resultant function or the ut would look like something like this. Okay, a function which is actually decreasing in the amplitude, all right, but it's still sinusoidal or still harmonic. I should not say sinusoidal, but it's still harmonic. Okay, so I can plot it something like this. Okay, so the amplitude is decreasing. Okay, and this is my u of t, and this is actually t on the horizontal axis. All right, so this is the plot of this function. Now compare this to the function I had here. I did not have any kind of oscillation here. However, in this case, I get an oscillation because of this term, the sine and the cos term that I have here. Okay, so for this condition, when this is satisfied, I get an oscillation, right? And I can represent my function or the response, the displacement response, as this, where the amplitude is actually decreasing with time, which is due to the damping of the system. All right, so for a damped system, the amplitude is not constant. Okay, and this here, the envelope curve, this can be represented as e to the power minus c 2m by t term. Okay, so it is decreasing at this rate. All right, so what I found out, that the term that I have here, C by 2m minus K by m. Okay, when it is greater than 0, I get no oscillation. So if you give initial displacement or initial condition, it would simply come back to its original position after a certain time. Okay. However, if this is smaller than 0, then I get oscillatory motion. Okay. Now what would happen if this is equal to 0? Well, if this is equal to 0, I would again get two negative roots here because this term would be 0 now. So the solution would still be similar to what I have here. So again, no oscillation. Okay, because there would be any complex term, so there won't be any sine and the cos term. Okay, so it won't have any kind of oscillation. Okay, so I should say now what I can do, if it's greater than or equal to 0, there would be no oscillation. So it would need to be strictly less than 0 or to have an oscillatory motion. Okay. Now for this case, what I'm going to do, equate this term equal to 0. Okay, that the C that represent this condition is actually the damping coefficient, right, at which there is a transition from oscillatory motion to non-oscillatory motion, and this C is actually called C critical. Okay, so at this critical value of damping, what you will see, the transition from an oscillatory to non-oscillatory motion. Okay, and I need to find out that value of damping coefficient. Okay, so I'm going to equate it to 0. Okay, so that gives me the value of C critical as 2m times A by m. Okay, and which I can further write it as 2m omega n. Okay, remember that there is a square root term here, so I can further write it as 2m omega n. So the critical damping coefficient can be written as 2m omega n. Now in reality, actual damping constant can be smaller than this or it can be greater than C critical, right? So I define a ratio zeta, which is the actual damping in the system divided by the critical damping coefficient. Okay, so the ratio of C by C critical is defined as zeta, which is called the damping ratio, or at many places you will also see that being referred as, damping as a value of the critical. Okay, so as you can see, in terms of C critical or zeta, what did we deduce here? We said that if C is less than C critical, or zeta is, or let us first say, let us just say that if this is less than equal to 1, I would have oscillation. Okay, and this is called underdamped system. Okay, so I will have an underdamped system here. When C is equal to C critical or the damping ratio is equal to 1, okay, I would not have any oscillation, so no oscillation. It is called critically damped system. Alright, it's called critically damped system. And when C is greater than C critical or zeta is greater than 1, I would again have no oscillation, and this is called over damped system. Okay, and if I try to plot the variation of ut for these three type of systems. Okay, so now I'm plotting ut, but now I'm dividing or like plotting it as a ratio of the initial displacement that is given to it. Okay, and this is t as a ratio of the time period of the system. Okay, so what I would see for each of these, let me just draw it. Okay, okay, so as we discussed, this is my underdamped system which provides me the oscillatory motion. So underdamped, zeta is smaller than 1. This is an overdamped system. Okay, so this is an overdamped system. So zeta is greater than equal to 1. And this is again a critically damped system. Okay, so this is a critically damped system with zeta is equal to 1. Alright, so this is the only three situation in terms of the resulting motion of a damped free vibration that are possible. Okay, so it could, so if you have a damped free vibration, okay, it would either be, if it's an overdamped system or if it's a critically damped system, there won't be any oscillation. If you provide it initial displacement, it would just come back to rest, okay, from an initial position, from the initial displacement. However, if it's an underdamped system, okay, then it would oscillate and then slowly or gradually the amplitude would decrease and then come down to 0. And at the rate at which the amplitude actually decreases depends on the value of zeta or the damping ratio. Okay, so I hope that is clear to you. Now in reality, most of the structure, okay, so the systems that are relevant to structural engineers like or the structures that are relevant to structural engineers like bridges, buildings, most of the systems are actually underdamped system. Okay, so let us say bridges, buildings, okay, other type of structure like chimneys, dams, etc. Most of these structure have value of zeta which is actually less than 0.1 or 10%. Okay, and those system can be categorized as underdamped system, and that would be the focus of study, okay, on this chapter, that we would be primarily dealing with underdamped system. Okay, but you could, I mean, in many cases you can see the example an overdamped system. So where an overdamped system would be useful, if you think about it, any system that you don't want to vibrate but you still want it to be flexible. Okay, so you want it to be flexible, okay, however you don't want it to vibrate, so it would have stiffness but it should not vibrate after you give its initial displacement. So one of the example would be a retracting door mechanism. So I don't know whether you have observed in many places in the classrooms or halls, you have actually a piston kind of thing that is connected at the top of the door, okay, which when you push the door, it allows basically the door not to vibrate a lot because there are a lot of people coming, like following you. So to make it safer, what do they have, I mean, that is one of the purpose, to make it safer for other people coming from behind you, or the other purpose is also to bring it back slowly to its original position. So that piston actually provides so much of damping that the system actually work as an over damped system, because we don't want it to vibrate back and forth. Once you push it, you want it to slowly come down to the original position. Okay, so an example of over damped system would be retracting door mechanism. And in similar scenarios, wherever you have something that you don't want to vibrate, but simply you want it to come back to rest after giving its initial displacement of velocity, you want or you would ideally like it to be an overdamped system. Okay, so like I mean, there are application of overdamped system, especially it would be more relevant to mechanical engineers or aerospace engineers. Okay, but for structural engineer, for most cases like building bridges, we are mostly focused on under damped system, and that is what we are going to study. Okay, so we are going to study under damped system. Okay, now we had obtained here the solution for, look at here, the solution for u of t here. Okay, but you can see there are two unknown constant. Okay, so those constant are c and d. So again the question becomes, how do I find these constant? And that again I would utilize the initial conditions u0 and u dot of 0. So let me just write ut as e to the power minus c 2m by t. Okay, c cos omega dt plus d sine omega dt. So I need to now solve this equation for the initial condition. But before that, remember I said my omega d, I am representing it as this quantity c by 2m square minus. So let us go back to the omega d value that we had assigned. Okay, so our omega d is actually not c by 2 but is actually k by m. So let me just correct that here. Okay, it is k by m minus c by 2m whole square. Alright, and I know my k by m is nothing but omega n square, correct? So I can write this as omega n square. What else is there? And if you remember, I wrote that my c by c critical I defined at zeta, right? And my c critical was 2m omega n. So c by 2m I can write it as zeta omega n. So this I can again write it as zeta square omega n square. Okay, so I can take the value of omega n outside the square root and I'm left with this quantity here. Alright, and this is called the damped frequency of the system. And this is different from the natural frequency of the system. Okay. Note that I'm omitting the term circular frequency, and that at many places we'll do that. Okay, I'm not going to every time pronounce the whole damn, the natural, basically the natural circular frequency. Okay, so if I say frequency and I refer, you just need to understand it like that. Okay, so omega d is related to omega n. The damped frequency is related to natural frequency using this damping ratio. Okay, now for the underdamped system, if zeta is less than 0.2, remember zeta square would be 0.04. Okay, omega d is approximately equal to omega n. Alright, keep that in mind. It is approximately, and I can also write, remember that using this relationship, my Td or the damped time period as Tn divided by 1 minus zeta square. Alright, so if you look at these expressions, for any non-zero value of damping, what I will have, the frequency is actually decreased, but the time period is actually increased. So due to damping, my frequency is decreased, but time period is increased. And by whatever small amount it may be, because as I said, if zeta is smaller than 0.2, it is approximately equal, the damped frequency is actually approximately equal to the undamped natural frequency. Okay, but theoretically it would actually lengthen the time period or increase the time period but decrease the frequency. Okay, so let us now plot the damped response versus undamped response. Okay, and that we can do after I have solved this equation, the equation that I have here for the unknown constant. Okay, so let us do that. I have these two unknown constants. Okay, and I'm again going to write, now know that C by 2m now can be written as zeta omega n. So I'm going to write ut as e to the power minus zeta omega n t, and inside the brackets I will have cos omega dt plus d sin omega dt. Okay, remember that the damped system is actually vibrating with omega dt, this frequency, because sine and terms are sine and cos terms have omega d frequency, so it is actually vibrating with omega d, not the omega n. However, the term here outside, the exponential term, it is omega n. So many times students while writing the equation get confused. Okay, that's why I'm doing this derivation, so that you don't have to remember anything. You can pretty much derive all the equation by yourself if you tend to forget it. Okay, now let us utilize this equation. For that, first I need to differentiate this equation once. So I'm going to use differentiation by parts. Okay, so I'm first going to differentiate the exponential term. This term would still be the same. Okay, and then I'm going to differentiate the parts that I have inside the brackets, which would give me minus c omega d. This would be sine omega dt plus I would have d omega d times cos omega dt. Alright, so let us substitute the value, the initial condition. So u0 is equal to 1 times c times 1 plus 0. So this equation gives me the value of c as u of 0. Okay, now let us take the second equation and substitute the value of t is equal to 0. I get that as minus zeta omega n. Alright, and then I will have inside the brackets c plus 0 plus 1 times, again I have 0 plus d omega d. Okay, so from this equation and substituting the value of c as u of 0, I will get the value of d as u dot 0 plus zeta omega n u of 0 divided by omega d. So now I have obtained both constant. So finally the expression for the displacement response of for the damped free vibration can be written as this exponential term here, okay, times u0 cos omega dt plus u dot 0 zeta omega n u of 0 and sine omega of dt. So this is the expression for displacement response of a damped free vibration. Okay, and I mean you can look at from here that if zeta is equal to 0, so if you substitute the value of zeta equal to 0, this system actually transforms to free undamped free vibration, right? Because this term would become equal to 1, and then the second term would be equal to 0, and omega d would be basically omega n because zeta is 0. Okay, so that I can just verify from here. But for a undamped free vibration, there is no damping, so amplitude is actually constant, it is not changing. However, I have an exponential decreasing term which would be non-zero if the value of damping is non-zero. Okay, so that amplitude of damped free vibration actually decreasing with the time. Alright, so if you plot it, undamped free vibration or damped free vibration, it would look like something like this. Okay, let me just try to plot it here. So let us say this is undamped free vibration. So constant amplitude. Alright. And for the damped free vibration, it would be something like this. So if you see, the amplitude is actually decreasing. Okay, so it is actually decreasing like this. Okay, so this is undamped and this one is damped. Okay, one thing that you can observe from this plot, that the time period Tn, which for undamped, let us say describe it like this, and for a damped I will describe it using, okay, let me just describe it here, these two peaks for the damped system here. Okay, depending upon value of the zeta, they might be close or they might be different. Okay, that all depends on the value of zeta. Okay, now comparing the response, we can see that if a system has very high value of zeta or very high damping, the amplitude would decrease much faster and it would come to the original position, okay, much faster. So the time taken to come to the zero position would be much smaller. Okay, and if you keep on increasing, then it would reach a point where it would become critically damped and it won't vibrate at all. Okay, all right. So once you understand this, okay, you can obtain the response of the system. All right, you can obtain the response of the system using the expression that we have derived. Okay, so uh, we are going to conclude this class at this point of time. All right, thank you.